Hello, welcome back to the course on polymeric biomaterials. Now we have started looking at structure property relationships in polymers, and earlier we have looked at definitions of words like mer, oligomer and polymer. We have also looked at what a repeat unit is and how that can be different from a monomer. In today's lecture we will continue from that theme and start to now look at more structural properties of polymers and how they can impact some bulk properties as well. So, in this lecture we are going to be looking at molecular structure of polymers, and by that I mean we are primarily going to be looking at concepts related to what the backbone of the polymer is, which we also will call a chain. We will also look at N group, which comes at the end of a given chain. We will also see how some polymers can have side or pendant groups, and the nature and type of the pendant groups can impact how these chains can pack together. So, we will look at that. Then we will also look at how you can also have copolymers where there is more than one monomer involved. And in the second part of this lecture, we will look at how some of these chain structures get fixed during synthesis under the broad umbrella topic of what we will call configuration of the polymer, under which we will look at a few different dimensions to configuration, where we will be looking at how repeat unit placement, isomerism, particularly optical isomerism, and tacticity as being different dimensions using which we can think of configuration. So, with that we will first get started with what do we mean by the backbone of the polymer. This is a word you will hear very often in polymers, backbone or chain. Backbone simply refers to the main linear chain where one monomer covalently links to another monomer. So, earlier we saw that the polymer chain is formed by linking of monomers through covalent bonds, and that linear linking of chains is what is typically called the backbone of the polymer. In many cases we will refer to the backbone as the polymer chain. And in any given polymer, either in the solution or in the melt state or in the processed solid state, you will have many such chains interacting with each other in different ways. How those chains interact with each other we will look at in subsequent lectures. Remember that the focus of this lecture is a single chain, that too the different parts that make up the chain. If you have the same monomer that is linked together through covalent bonds, and that is typically called a homopolymer. One example of that is polyethylene, where ethylene is the monomer and the repeat unit is simply this. So, this just keeps repeating n number of times to lead to that long chain, where if you now have the polymer denoted here by n, which is the degree of polymerization, which simply tells you how many such repeat units are there in that chain. You can also have different monomers. One example that would immediately come to your mind is that of proteins. Now, these are known as heteropolymers, where the words hetero simply indicates that the main chain is not made up of a single monomer but multiple monomers, and proteins are a good example of that. You have different amino acids making up a long linear chain of the protein, and that would be considered a heteropolymer. Another popular example in biomedical engineering of a heteropolymer would be this polymer called PLGA, polylactide co-glycolide, where you have both the lactide and the glycolide units repeating in the backbone of the chain, leading to a heteropolymer which we know as PLGA. Now, one advantage with understanding this chain structure or the backbone structure is it helps us classify polymers based on the functional groups present. So, for example, I am showing you two examples here. One is on top we have seen is a siloxane. More commonly or more specifically, this is polydimethyl siloxane, which is an inorganic polymer. which is different from a hydrocarbon based polymer, which is typically called an organic polymer. Now, one example of an application in which this is used, we have earlier seen that PDMS is used as implants for breast reconstruction. One example of that is post-mastectomy reconstruction of the tissue. Shown below is an example of a polymer called polyethylene terephthalate, where you have the terephthalate group and the ethylene group, leading to a long chain again, and hence the name polyethylene terephthalate. This more commonly called PET, and one commercial version of this is called Dacron. And oftentimes you will find people using these terms interchangeably, but remember that PET is the most generic word to use. Another common example where these words are interchanged is Teflon and PTFE, where Teflon is a commercial version with a specific set of properties, as opposed to PTFE, which is a more generic name, which is polyethylene, polytetrafluoroethylene. So here polyethylene terephthalate, also commercially called Dacron, one example of where it is used is in ligament reconstruction. So if you have heard of sports injuries, one ligament that is often injured is called the anterior cruciate ligament, ACL, and PET is often used for reconstruction of injured ligaments. So that in some sense should give you an idea of how we can think of backbone, and notice that here, because of this group, this now becomes a polyester, which is a classification for the polymer based on the functional group. Likewise, siloxane for this. So the backbone itself allows you to classify polymers based on the functional groups. Next, we look at something called the end group or terminal group. Now, the end group is typically the functional unit that lies, as the name indicates, at the extremity of a polymer chain. So you notice that it was important for us to define the chain or the backbone first, because everything else, end group and later on side group, etc., will be defined in relation to the backbone itself. The functional unit becomes very important for reactivity. The end group that is there for a polymer, if it has a certain functionality, it can react in a very specific way, and we will look at an example very shortly. End group is typically useful in determining the degree of polymerization, also called N, which is simply the number of mers, average number of mers in a polymeric set of polymeric chains. So it can either be done using NMR, or you can use a titration method for molecular weight determination, essentially a technique where, based on the N group, if you have an acid N group for example, you can titrate it against an alkali, and you find the number of moles of alkali that is used for titration. If you know that, you get information about the number of moles of functional group present, and if you know the sample mass of polymer that you began with, from this you can do a simple set of calculations to determine the molecular weight simply based on the N group. But there is a clear limitation here. This approach will not work for molecular weights that are quite large. In fact, this approach will work only for very low molecular weight materials, because the N group that are there, as the polymer chain keeps growing, you get lots of different atoms joined or molecules joined together, the number of N groups that are there becomes very, very small. So, this technique is not very sensitive when you have very long chains or very high molecular weights. So, shown here is an example of a polymer with a functional group at the end, which looks a bit different from the polymers that we have seen so far. So, I will first talk about what the middle portion is. That is simply polyethylene glycol, that is CH2, CH2O. It is a very popular polymer developed primarily for in the 80s and employed in biomedical engineering for non-fouling applications. So, that is polyethylene glycol, but what you see at the ends are two different, they are the same functional molecule at functional group at both ends, but it is different from the one in the middle. This is together they are called the diacrylates, right. You have functional groups at both sides, making them diacrylates. Now, this, as it turns out, is very useful. If you remember, I said that the functional unit can have specific reactivities based on the type of functional unit you have. This can be used for photo cross-linking. So, you have acrylate or methacrylate or diacrylate groups. The double bond there is of significance. These double bonds are special because when they are at the ends in the form of acrylate or methacrylate groups, or in this case diacrylate groups, in the presence of a photoinitiator, it can undergo something called a free radical polymerization, which we will look at in more detail later. Which can then help form a cross-link network. That is why it is called photo cross-linking, because the trigger for that is light. You have a photoinitiator and you shine UV light of a specific wavelength, then the reaction begins, which is called a free radical polymerization reaction, and that leads to a cross-link network. So, at this juncture, I would encourage you to pause and look up how photo cross-linkable hydrogels, for example, polyethylene glycol diacrylate, are used in biomedical applications. It is a very fascinating set of applications, right from encapsulation of cells to understanding how cells interact with hydrogels, to controlled release applications, to tissue engineering. There is a whole gamut of applications for which photo cross-linkable gels can be used for, and PEG diacrylate is just one example of them. Again, to highlight where we are in the course, all of that comes from the end group itself, and that is a very important point to note here. End groups, as it turns out, can also have or dictate the degradation properties. For example, this polymer PLGA, which we talked about on the previous slide, it is a polymer with two units, the lactide and the glycolide unit. It is a copolymer, and when you commercially procure PLGA, the company will typically ask you, do you want acid terminated or ester terminated PLGA? Now, acid terminated PLGA allows faster access to water, and hence acid terminated PLGA chains will degrade quicker, as compared to ester terminated PLGA chains, everything else remaining the same, the molecular weight remaining the same, the lactide to glycolide ratio remaining the same. Acid terminated PLGA allows faster and quicker access, easier access to water, and hence it leads to hydrolytic degradation of the backbone, which also we will look at later, as compared to ester terminated PLGA. So, you see, an innocuous group such as the N group can have far reaching consequences in terms of something like degradation, which you can think of in bulk as well, and all that goes back to this innocuous side N group that is sticking to the terminal part of the chain. Next, we will look at another related idea, again in relation to the backbone of the chain itself, which is the side group or the pendant group. They go by different names. These are atoms or functional moieties that are attached to a backbone chain, they are not on the end, they are attached to the chain itself. What is important to note is they are not the chain themselves, and hence it is not correct to think of them as either oligomeric or polymeric. They are just side groups that stick out or hang, they are called pendant groups. So, one example of that shown here is polylactic acid, for which the pendant group is simply the methyl group. And it turns out, if you look at the structure of polyglycolic acid, it is this methyl group or the absence of it is what distinguishes the lactic versus the glycolic acid. So, I would encourage you to look up the structure of polyglycolic acid and compare and contrast that with polylactic acid to convince yourself about the differences. What I show on the right is polymethyl methacrylate. The significance of the side group will become more and more clear as we go through the course, but for now let me just point out that if you have very bulky side groups, if I have a chain of polymer and I have another chain here, now this chain, let us say, has a group like this, and that group keeps showing up again and again, as opposed to this polymer where there are no such bulky side groups. Now, as you can readily imagine, in the first case, the chains can come together spatially more easily and can pack more tightly, whereas in the latter case, chains are not going to come together that easily. The packing is not going to be that tight because the bulky side groups are going to provide steric hindrance. And from there, you can extrapolate and show that that will have a direct impact. This packing will have a direct impact on a property like crystallinity, which will in turn have an impact on mechanical properties and perhaps even optical properties. Again, the idea here is, although we have not defined the term crystallinity formally, and we will have entire lectures dedicated to that, idea here is to get used to these terms early on in the course so that you can appreciate the jargon in different contexts. The limited point I want to make here before we move to the next slide is that the side of the pendant group, again, you are looking at a chain and looking at what sticks out, but you see how large of an effect it can have on things like crystallinity, mechanical and optical properties, a lot of which are bulk behavior, macroscopic behavior that you can measure actually. Now, we now look at another related concept called copolymer. As I said earlier, copolymer is simply two or more types of mers or monomers in each chain. So, depending on the arrangement of the mers, you can have different types or versions of the copolymer. For example, a random copolymer is simply one where the repeats are statistically random along the backbone. The fact that one monomer has been added before will not dictate largely what the next monomer is going to be. That is what we mean by statistically random. So, that means something here. So, an example of a structure that would result that is one example of a structure that could result from a random copolymer kind of a polymerization kind of a procedure. You can also have alternating copolymers where the monomers are placed on alternating positions along the backbone. Again, you see, we are talking about the backbone itself here. So, here this will look something like this, where A and B are the two mers. You can also have something called a block copolymer, where the monomeric units of one type are grouped together in what are called blocks. This grouping they call blocks. So, you can have something like and so on, where each of these would be considered a block. You can also have along the same lines something called a graft copolymer, where you can have a polymer that is a linear chain as we have seen, but you can also have along the backbone in some parts a branch that comes out. For example, this is the linear chain or the backbone. You can also have branches coming out this way, where the branch is a different mer. So, you see, just based on having more than one mer, you can have multiple types of copolymers depending on how the mers are arranged along the backbone, and in this case, the last case, where you can have grafts coming in, where that can give specific types of functionality. Now would be a good time to pause and look at PLGA in slightly more detail, which, as we have already seen, is a very important medical copolymer. So, shown here is the structure of the PLGA. Right away, what you realize is the polyester. The ester group is very prominently seen here. This is the lactide unit. This is the glycolide unit. And PLGA has a bunch of interesting properties just because of the fact that you have two mers or two monomers forming the polymer. Depending on the ratio of the mers and depending on whether it is acid terminated or ester terminated, as we saw earlier, PLGAs can exhibit a wide range or spectrum of properties. So, like we saw, it is a random copolymer of the lactide and the glycolide acids. Interestingly, both of those are present in the body as part of different metabolic pathways. So, lactic acid and glycolic acid are naturally present in the body as part of different metabolic pathways. And it turns out that PLGA is a degradable polymer and it undergoes degradation through ester hydrolysis. That is the dominant mechanism, which we will look at again in more detail in a future lecture, but for now it is important to just keep in mind that PLGA is an polyalpha ester which can undergo ester hydrolysis, which means the backbone is susceptible to degradation upon contact with water. Now, the degradation products, as it turns out, will be lactic and glycolic acid, and that is a useful feature because not only is the polymer itself cytocompatible, the degradation products are also okay, as they are going to be excreted by the body and not recognized as foreign. As far as the copolymer itself is concerned, you will find different varieties of PLGA. If you just look up PLGA, you will find 85-15, 75-25, 50-50, these are different types of PLGAs. What the numbers simply indicate is the lactide to glycolide ratios. So, 50-50 will have equal number of both lactide and glycolide. And as you will see here, the degradation of 50-50 is faster than 85-15. What that means is, I can use different types of PLGA based on the L to G ratios depending on the degradation rate that I want in my application. And lastly, what is important to note here is copolymer properties are always uniquely determined. Just as a case in point, PDLLA, which is the DL version of the lactide polymer, is completely amorphous, and PGA, which is the glycolic acid polymer, is highly crystalline, whereas PLGA, which is a copolymer of the lactide and the glycolide, is completely amorphous in both the 85-15 and the 50-50 versions, which are very popular. And PLGA is quite often used for many control release applications. It is also used in many clinical applications for its high tensile strength, flexibility and controlled degradability. One downside, potential downside of this polymer is the presence of acid degradation products, which can lead to a localized decrease in pH, and that can have certain biological consequences, not serious, but it can. But PLGA, the degradation also is autocatalytic, which means the more and more of this is produced, the faster it will degrade. So, there have been approaches that people have looked at in the literature to see if you can add some components to PLGA that will neutralize that effect. So, this is one thing to keep in mind when working with PLGA. Now that we have looked at the chain itself, N group, side group and copolymer, we will now move on to a very important concept in polymers called configuration, which again relates to the chain and the relative placement of different groups along the chain. Configuration can take many different dimensions, and we will look at a few dimensions in today's lecture. But one thing that is important to note here is everything I have talked about so far in this lecture, right from how the chain is formed to how the N group functionality exists, to how the side groups are attached, to grafting of other mers to the backbone of a different mer, all of this is fixed during synthesis, or what is more commonly called polymerization. So, while it is important to realize that we are looking at structure property relationships, and more specifically in this lecture we are looking at the polymeric structure itself from a single chain perspective, it is important to realize that that is fixed during synthesis. A large part of it is fixed during synthesis. And so, configuration is no different. Configuration of a polymer is fixed during synthesis and cannot change very easily. Configuration, like we just saw, cannot be changed without breaking primary bonds. So, the primary bonds that make up the polymer itself have to be broken in order for you to change configuration, and that is not easy at all. So, configuration is largely fixed once the polymer is synthesized. Another word that you will often come across with polymers is this word called conformation. You will often hear this in the context of proteins, protein conformational behavior. Unlike configuration, conformation can be changed and it can be reversed also in many cases. For example, for many proteins you can heat them and the conformation of the protein will change, because the bonds that are being broken there are not primary bonds but secondary interactions such as van der Waals bonds, hydrogen bonds and so on. And upon cooling and under certain conditions, along with the addition of chaperones for example, you can get back the original protein conformation. That is not at all possible with configuration. So, configuration cannot be changed due to conformational changes. And the configuration of the polymer affects ability of the chains to come together and pack closely and crystallize and form these ordered crystalline domains. And it turns out that that in turn can have an impact on properties like melting temperature, glass transition temperature for semi-crystalline polymers, and a whole host of other mechanical properties as well. So, broadly that is what configuration is in terms of a general understanding. Now, we will look at specific manifestations of configuration. So, the first manifestation we will look at is configuration referring to the direction in which monomers are linked. And one example of that I am giving you here is that of polystyrene. So, now what you see here are two different versions of polystyrene. One is called a head-to-head configuration. The other one is called a head-to-tail configuration, where this is called head-to-head because these two are meeting during synthesis head-to-head, whereas here it is head-to-tail because these two bulky groups are not present next to each other. And as you can guess very correctly, the head-to-tail is the thermodynamically and spatially preferred configuration, which means during synthesis most of what you will get will be the head to tail configuration. But as you clearly see, they are not the same, and the only way for me to get one from the other is to break the primary bonds, and that is not possible. Another version of or manifestation of configuration is this idea called stereoisomerism, which now has to do with the placement of the side group that we saw earlier above or below the carbon-carbon plane on an asymmetric carbon. So, I have mentioned a bunch of different keywords there, we will look at them one by one. We have already looked at what a side group is, right. It is a group that sticks out from the backbone like a pendant group. We will now look at what a CC plane is and what an asymmetric carbon is. So, the CC bond plane, while we are limited by how we can draw 3-dimensional structures on a 2D screen, you will have to imagine this in 3D, where the carbon backbone itself can have side groups on both top and bottom as shown, or in this case, you notice that we are showing the hydrogens, one with this, the full line, one with a dashed line, and that indicates atoms that are going in and out of your screen, for example. And you notice here that I have two examples. One, what I call a symmetric carbon, another is called an asymmetric carbon marked by an asterisk. A symmetric carbon here simply is a carbon atom where all the hydrogens are indistinguishable. Whereas in an asymmetric carbon marked by C star here, I have an R group here, which could be any group. In the previous example, it was the benzene ring in polystyrene, and depending on where it is placed, it can lead to D or L isomers. This is also called a chiral center. It has to do with how light interacts with these forms differently, whether it is placed above or below. So, each asymmetric carbon can exhibit L or D isomerism depending upon the placement of the R group above or below the plane, or in this case out or into your screen. Now, as it turns out, this can have some very interesting consequences. So, let us look at this in more detail by using the case of polylactide. So, we already saw that the asymmetric carbon leads to chirality, and you have the D and L isomers, which you would be familiar with from your chemistry classes. They are essentially mirror images of each other, and those have a special name called enantiomers, which are not the same. The DL and L versions are not the same. They are mirror images that are distinct from each other. Right? When I mean that they are not the same, compositionally they are exactly the same. So, they have the same composition, but the orientation, the 3D orientation of the groups, it is what distinguishes one from the other. And we are seeing here that the placement of groups on the carbon and lactic acid can lead to the L and D isomers. So, what you have shown here are the L and D isomers, which are mirror image enantiomers that are distinct from each other. Now, depending upon whether the polylactide is made from the L or the D or the DL together, you can potentially get 3 different versions of polylactide. So, you can have PLLA, where it is simply poly L lactide. You can have PDLA, which is poly D lactide, and you can have PDLLA, which will be poly DL lactide, where the first one is made up of only the L isomer, the second one is made up of only the D isomer, The third one is made up of potentially both isomers in some combination, typically 1:1. Now, why is this important? Why are we looking at this? As always, we are interested in how this can eventually affect properties that we are interested in. And as it turns out, this will directly have an impact on properties. I am just giving you an example of that. PDLLA is less crystalline than PLLA, which is semi-crystalline. And I have been using the word crystalline or crystallinity quite a bit in this lecture. For the time being, think of the word crystallinity as having to do with an ordered structure. So, you can have chains that have some kind of an order like this, as opposed to amorphous, where the chains have no particular order, they are just dangling around. And typically in a semi-crystalline polymer, you will have something like this, where you have a mixture of both amorphous domains and the crystalline domains. So, right away you see that PDLLA is less crystalline than PLLA, and PDLLA degrades much faster than PLLA. So, depending upon your application or your need, you can either use PLLA or PDLLA, all the while keeping in mind that they are all versions of polylactic acid. And typically PDLLA, because it is going to degrade faster, it is typically more often used in controlled release applications where you want drugs to release at a certain rate. Common applications of polylactide include facial volume enhancers. This is where polylactide is injected into regions in the face to enhance volume, and it is an interesting mechanism in itself. One way to increase volume is to use hyaluronic acid injections. Hyaluronic acid is another polymer, a charged polymer, where you have a lot of negative groups because of the carboxyl ion. It is a naturally found polymer which helps in lubricating the joints. So, that is often used, but that directly contributes to volume enhancement. But PLA is a slightly interesting version where the injection of PLA on its own can have a bit of volume enhancement, but it also causes localized inflammation, mild inflammation, which stimulates collagen production. And collagen is a protein, as we have seen earlier, a structural protein that forms the part of many soft and connective tissues in the body. So, the PLA injection leads to localized inflammation leading to collagen production, which in turn enhances the volume. So, this should give you a sense of how something as what you might think is as trivial as just a difference in the placement of the side group on an asymmetric carbon, but that results in such a large difference in properties such as crystallinity and degradation. The last manifestation that we will look at, a related manifestation of configuration we will look at, is something called tacticity. Now, this is another word that you will hear very often. You might have heard of things like isotactic, syndiotactic and atactic. All of them are different types of tacticity that polymers can take up. This also has to do with spatial arrangement of side groups along the backbone on asymmetric carbon, but now you are looking at it from the perspective of the ordering itself, and you can give them different names based on how the ordering is. If it is highly ordered, you call it a certain, you think of it as a certain way. There is no order, you think of it in a certain way. And as we have already hinted, that ordering or the placement can have a very large impact on how the chains can come together or crystallize, and how that can in turn affect the bulk properties. So, we will take the example of polypropylene, which we have not looked at so far much. It is very commonly used as a mesh in hernia surgery. It is known for its excellent mechanical properties, and most of the polypropylene that is produced is what you would call isotactic polypropylene. And what is that? So, what you see here is you have the asymmetric carbon here in polypropylene, And what you notice is the side group, that is the methyl group, on the asymmetric carbon is placed all on the same side. And remember that this is configuration, so it cannot be changed post hoc. It is fixed in situ during synthesis. So I used two words which you will often hear in the scientific literature. I would encourage you to look up these words and get familiar with them. So like I said, you can't change the configuration post hoc. It is fixed in situ during synthesis. So a version of polypropylene where all the methyl groups are on the same side, placed on the same side, is called isotactic. Now right away you see that there is some order in the structure, which means we just saw that crystallinity has to do with order. So you can now maybe able to connect how this can lead to higher orders of organization in the polymer itself. So tacticity, which is just the placement of the side groups along the backbone, leading to higher order and arrangement, and that leading to differential mechanical properties, as opposed to syndiotactic, where the arrangement is alternating. So every other asymmetric carbon will have it either on top or on the other side. So the arrangement just alternates. And atactic, of course, is lack of tacticity, which simply means that there is no particular order to the placement of the methyl group itself, right. If you zoom in too much, it may seem like there is some localized order, but if you zoom out a bit and look at a large chain, you will see no particular order for atactic polymers. And as it turns out, tacticity, like I said, affects the regularity of the structure, which in turn influences the rigidity, crystallinity, and even things like melting properties and mechanical properties of the polymer. So isotactic polypropylene is primarily used in many applications, including medical applications, primarily because of these reasons. So with that, I hope you've got a good sense of molecular structure, including configuration, where we have looked at the chain, how you can have different groups placed along the chain, how you can think of the N group, and also what is meant by copolymer, and finally looking at different manifestations of configuration which we distinguished from conformation. In subsequent lectures, we will see how some of these can now lead to, when you zoom out a bit and coarse grain a bit and look at the polymer from slightly more zoomed out picture, how this can affect other properties in subsequent classes. Thank you.